We are going to talk a little bit about the word static, how can we use it in classes. And then we're going to start with the big block of lectures that's going to be kind of under one big name, memory. Because C++ allows you to work with memory, well, not directly, but close to directly. And I think it's an important skill to understand what is going on. It's not that much of a practical issue here, so most of the things that I will be teaching you in this lecture are just there for you to be able to return to this lecture whenever you don't understand something. So it's not something that you need to keep like in your active baggage most of the times. So this is kind of like the basics of what we already know, like how things that we already know, like vectors, strings, and so on, how do they work under the hood? Yeah, right. So that's that. With this, I guess we can start. So let's start with static. There is a word static that you can use in whenever you define a variable. And we will not go deep here into using static without classes, but we will talk about using static in classes. Like in classes, static can be variables and methods. Both can be static. It's just a definition. So usually you write like int something, which is a return type, and then like a name of a function. This time you will write static int something. And we will now understand what it means. So the idea is that if you define a member static, like a class member, so say you have a data member, whatever, integer x, and you want to say it's static. So usually if you define like integer x in a class, it exists once per object of this class, per instance of this class. So whenever you create multiple objects of the same class, they will have their own this integer x. If you declare this integer as static, it will exist exactly once per class or per type, not per object, but per type. We're going to see it on examples, but this is what kind of, if there is one thing about static, it means that it, like in classes, it exists once per class. Right, so this value is equal and shared between all instances. So all instances can equally use the static variable, and if one instance changes this value, the others will also have this value changed. And they must be defined in the CPP files. So you will be tempted to define them in header files a lot. Don't do that. The rule that you need to remember is they always must be defined in a CPP file. Right. So that was the static members, like static variables in the classes. Now, if we talk about functions, it's relatively similar. The idea is that you can call this function without having a member of, without having an object of a particular class. So you can use something like a syntax that looks something like this. You tell it's a function within this class, say class name, and then you say, well, this is my function, and then you give some parameters. And we're also going to see when it can be useful. Mostly, you have to think of, does this function belong to this class? If yes, then it needs to be a function of a class. And then you need to decide, should it be a static function or should it be a normal function? And you have to think, does it have to know about anything within a particular object? If it doesn't have to know anything about the information in a particular object, it probably should be static. Otherwise, it should be a normal function. But then again, examples are for that. So speaking of examples, first of all, let's start with the static variable to show you that it's actually shared across all the instances of a particular class. So let's say we have a class, or a struct in this case, but I hope at this time you understand that structs and classes are kind of the same. The idea is that we define a type counted. So it may be a silly name, but for illustration purposes, it must fit on the slide. So bear with me here. And it has a public static integer member count over here. Again, what you usually do when you declare a member of a class, you give it a value. And you cannot do that here because it's a declaration of this member variable. So you must define it outside of the class. That's the rule that you need to obey when you're using static members. And that's why we define it over here. So we say, okay, our counted count is 0. And this way we have completely defined our static member variable. So why is it used? Like we can use it to count the number of instances of an object. So let's say we want to make sure that we want to know how many of counted objects are there in our program right now at any point of time. And for that we can always just print this count. And so I urge you to try this out at home. Again, like as always, copy paste, run it, see what it does, change it, and so on. This way you will learn much better. Right, so in this particular case, you create 2 objects, then you output count, it will output 2. And when you create a third object, it's going to be, the count will come up to 3. And that's because whenever we construct a new counted object, we increment the count, and whenever we destruct this object, we decrement the count. So we have exactly 1 count variable for all of the instances of this class. Does it make sense? So who is completely fine with static and understands why it's used for member variables? Okay. Good. The ones who don't, let's try to figure out what is confusing to figure it out now instead of making you lose time later. So is it clear that static variables exist once per class and not per instance? Is this phrase clear? So who is fine with that? Okay, well, majority of people is fine, so I guess it's good. Then, is anybody confused with the constructors and destructors? So who still is confused with constructors and destructors? Like, okay, anybody else? More people? 1? You can come later. I can explain it, no problem. But I just want to find out what I need to repeat now. Okay, so is it like more that you are just not trusting yourself because you didn't try it out yourself and that's why you are not completely content with it? Okay, good. Then there is nothing that I need to repeat now, I guess, and you just need to try that thing out. Good. So I hope, at least to some degree, it's clear what the static variables do. So let's switch on to static functions. And, oops, it doesn't completely fit on the slide. Sorry for that. The only thing that is missing is just the curly bracket there, so I hope you trust me on that. Let's define some very stupid class point. So it's usually, a lot of programs have the class point, and many of them define it on their own. And we're going to do the same thing here, and it is a very stupid class over here. But the idea is that it has some member variables over there. So it's a point, it's a 2D point, it has an x and it's a y, and they're integers because why not? And what we want to do is we want to be able to compute the distance between 2 points. And we could theoretically just do a function that would compute the distance as a simple function. So for instance, we could just say, make this function not static and take like the other point. This way okay, I think it's again easier to just do a example again. Okay. So class point, int x, int y, private Okay. Oops. All right. So we have a point now, and we want to do something useful with it. So we probably also need a main, and let's say that we can create a point A of 1, 1. Okay, good. So what we want to do is we want to find distances between the points. And the typical way we would do it is we would say, well, okay, what is the distance from this point to another? And for that we would write a function, something like float distance. And we would say, well, it will take another point because that's what we want to find the distance towards, right? It's probably going to be const because it doesn't change my object. It just needs to return me the distance. And what will it do? It will basically just find the Euclidean distance between them. So let's say there is the x difference. It's going to be my x minus other x. And we are in a function. So in this function, we can call any private members of another of the same class as we want to, because we are inside of the class. We trust ourselves when we are within the class. Good. So that's why we can use not only our private member function, our private variable, but also the private variable of the other. And let's do the same thing, but for y. And now we want to return a square root of x diff squared plus y diff squared. Okay, and we need to include, as usual, iostream to print something out, and include cmath to make sure that we can use sqrt. So the sqrt is just a square root function. Good. Okay, so I will be using the namespace std just to save space. And what we can do now is we can create another point B of 2 and 2, and then we can say A distance B, and we can see out it. Distance. Okay. So if we run it, I hope you see that it prints out the distance, which is whatever, a square root of 2, which is correct, right? So it's a diagonal between 1 and 1 and 2 and 2, so at least we've implemented our distance functions correctly. I can't tell you how many times I've implemented this function wrongly. Like when you do like one small issue and then you spend a week of debugging and then you find that you've implemented the distance functions wrongly, and that's why the results are wrong. So having one function instead of having many of them is very helpful. Like, that's why I was forcing you to know like classes, functions, and so on. The more you encapsulate, the more you reuse, the less chance you will make a mistake. Good. So at this point, it doesn't really look kind of what we are used to, right? We're used to saying, tell us the distance between these two points, and not say, point, get me distance to another one, right? It's just not the way we think about it that way. So what usually we can do is we can use a static function. So we can say static float distance, and because static function doesn't take our object as input, so for instance, this function takes our object x and y as input by default, so it's already there within this object. But we don't have an object anymore, so we cannot use x underscore. So that's why we will probably need 2 points. whatever A and let's say a point B. And again, this function, we don't need to put const over there because there is no object to change. So it doesn't have to guarantee that it doesn't change an object, even though it doesn't, because there are no objects that it implicitly has, right? I hope that makes sense. So what we can do now is we can return, I mean, we could implement the whole distance function over and over again, but what I want to do is I can just use the distance function to B, and so we're going to reuse our function from, so we're going to reuse this function here. Okay. Good. So how do we use this function? It's kind of very simple. We now have to say that, so this function, the benefits of using the static function instead of a free standalone function, they behave exactly in the same way, but the idea is that now we explicitly say which class does our function belong to. And this makes all the difference, because now, again, whenever you work with points, you expect all of the operations on the points to be within one class. So if you want to define distances between 2 points, this function should be in the same class, or at least in the same file. But while it can be in the same file, this way you explicitly say it works only on points. So that's why it belongs to the class point. So what we can say is, we can say point, distance, and then we say from A to B. And I argue that, at least in my head, this is a much more readable syntax. It tells us, well, it's like we say, we take the class point, and we want a distance from this class point, and then we give 2 inputs to it, which are probably points, and that will give us the distance from point A to point B. Okay, so if I run it, you can see that it works. There are 2 distances exactly the same. So that's kind of what the static functions are all about. There is nothing else to it. Sorry. Okay. Any questions to this for now? Yeah.
How is it running time-wise? Isn't it slower?
No, it's not slower. It's exactly the same. I mean, it's just a function. I mean, probably the compiler doesn't care if it's static or not. For it, it's basically, as far as I'm concerned, it's just syntactic sugar. So it's for you, like it's for you to read your code better. Because, I mean, in this case, you can do a distance function, but in some cases, it just doesn't make sense to have a typical function in a class. It does make sense to bind the function to a class to some degree, but your alternative, if you wouldn't have a static function, would be to just have a standalone function. And a big plus of a function, of a static function, that can still use all the private members of your objects. So I can easily write something like cout AX, for example, and this will still work because I am still within the class, and I can still. So I'm within the class, I'm not within the object of this class. But because I'm within the class, I can still use all the private members of any object of my class. Does it make sense? And this way, if I needed to, so alternative to this static function would be to have it outside of the class. And this way, I would need to make sure that my objects have a proper interface that I can call, like an interface, I mean public functions, that I can call to do my functionality. And sometimes having that, like, so I would need to call like a getter to X or a getter to Y and so on. And if I do a getter, it will do a small copy of a small int, which probably will be optimized by the compiler anyway, but it's kind of, we rely on a compiler here. And this way we guarantee we just use that variable, right? We're not returning a copy of it. Okay, I hope that made some sense. Any other questions to this? Yeah?
Why do you use the static
Not really. So let's try that. Let's remove the static. What does it mean? It means that it still has, so, okay, there is a really good explanation if everybody is comfortable with Java, but if not, I will try the other way. Okay, so like, who is comfortable with Java? Okay, not enough. Okay, then the idea is that whenever you don't have a static function, you have an object of your class. And this object is, you can have it as, so for instance, here instead of x underscore, I could write this x underscore. It's exactly the same. We didn't do it yet because we don't know what pointers are yet. We will start knowing it today. But the idea is that this means your object. So the one that you're calling this function from. So if I call a distance b, this in this function will be a object. Okay? So whenever I don't have a static function, I must have an object. If I don't have an object, I cannot call this function. So in this case, if I remove the static over there, oops, sorry. If I remove the static over here, then suddenly this function, it takes two points as input, but it also needs another object which it has to be called from. And this way, we cannot call this. This is an error. It will tell us something like, yeah, so call to a non-static member function without an object argument. So the compiler is again our friend. It will tell us that we're doing something wrong. Yeah, that's basically it. So that's why static should have been there. Yeah. Again, feel free to try it out, see what works, what doesn't. And there is no rule when to use static functions and when not to use static functions. At least I'm not aware of one. It mostly comes down to what is more readable. So you should really think about your code being readable. Code is generally more read than written. So you write it once, you will have to reread it at least a couple of times. Like you maybe will forget how you implemented this function. Maybe you will have to read again through it. So at least, like even if you're coding on your own without other people, it's a kind of a good assumption that every code, like every line that you write will be read at least twice, at least. And you should really optimize for reading. Like, so you should make sure that whatever you write makes sense so that you can open it up in 2 months, not remembering what you've done there, start reading it, and still would understand what it does without going into every function and figuring out what happens there. Yeah?
In this example, we have to change point on line 26 to a dot distance.
So to fix it, it would be, yeah, something like, we can very funnily do this. It will be, it's very stupid, because this is very confusing. Like if I read this in the code, I will be completely confused what the person meant. Because it doesn't tell me what it uses this object, but then it uses it again here. How is it using it? Like, then I have to go into the function, find out what is done there, find the person who did it, and explain them that they were wrong, right? So make sure that your code, like, this is readable syntax. It says, find me a distance from, like, I basically ask A to give me distance to B. It makes sense. And this syntax doesn't, but the syntax with a static still does, because I basically say, hey, class point, give me the distance between these 2 points. Okay? Yeah?
Why do we not need the static in the main function?
So you can use static outside of classes. We will probably not go deep into that because it's not really useful for this course. But the idea is that whenever you say static, it means that it must be... I can't really explain it well now, because it needs a lot. To explain it well, I need a lot more knowledge from you than I gave to you in this course, so I don't really want to confuse you at this point. You could put static here. I could give you a link to read about it if you want to, but the idea is that you don't need static here because this is just a normal object. And this normal object has all the normal functions. This object doesn't care about any static functions in its class. The only one who cares about static functions in the class is the class itself, or the type, so like point. Point is our new type, and this new type cares about having static functions. That's the only thing that can call static functions. So if I go back to having a static thing, you can say that it's not entirely correct to say that, but it's a way of understanding it, of saying our class point calls function distance. It's not really true, but the only entity that needs to care about having static functions is the type, or the full class, not the objects of this type. And this is the main difference. So whenever you say static, you say, forget about objects, I only care about my class. And all the other functions, they care only when they are there, only when the object is there. Hope that kind of was clear. It's hard to explain. It's probably, just try it out. Try to make different functions static, see what breaks, and see what syntax can you achieve. Like, see what can you write with it. Like, can it be more readable? Can it not be more readable? And stuff like that. Good.
Can we do a void main function?
The what?
Void main function.
You can do, yeah, you can do a void main function. It will still work. It's not a good idea to do it because main function actually expects you to return an integer because that's your error code. I don't really know how system handles it if you have a void, because it doesn't return then anything. I think it always returns 0 by default then, but I'm really not sure. It's probably not even undefined. It's probably defined, but I just don't know how. And again, there are so many things that you can do in C++ that you shouldn't really focus on what can you do, but rather to learn one consistent system that kind of makes you go over the typical pitfalls. So whenever you're doing something that doesn't really make sense, so say like return void from a main function, you know that any function, like a main function, must return a error code because that's what the shell expects it to do. And if you pass void, then you're kind of in this gray area where you don't really know what's going to happen. And this is not a really great idea because then you have to learn really quickly what is going on and why is it going on. And usually the under the hood of this is pretty complex. So you can, but you shouldn't. Good. So static is relatively simple. That's everything you need to know about static in classes, really. Like if you learn this, if you do these examples, that is exactly the way it's used everywhere in any other program. Good, so now we go to the memory world, and we are going to understand how all those like vectors and strings and so on operate, at least to some degree, and how does it relate to the actual bits in our memory and so on. So we're going to talk about it. It is going to be a bit scary. A lot of things will be scary because we are going to talk about representation of the numbers in memory, but remember that you don't need to learn it. Like, you don't need to know it by heart. Every time I need to prepare this lecture, it's totally fine if you need to look up some things. The important part of this lecture, the takeaway message, is this is the place that you need to go back to when you understand that you have an issue with representation in memory. And this is it. So for example, a bunch of people in the first homework or in the second homework had issues with the histogram because it wasn't returning 1 when it should have returned 1, but it was returning 0.9999998 something, right? So that is the issue with the fact that float has limited precision, and the precision comes from well-defined structure. Like we know exactly where the precision is lacking, and we know exactly why. And this is what I will explain to you now. And again, you don't have to, like, we will not ask it on the exam. We will not tell you, hey, okay, so how many bits does the, like, whatever, like float, like is float represented with, and what's the precision if I add like 10 million to it or something. You don't have to know it. You have to know where to look for it when you need it. And you have to understand the moment when you need it. Okay, I hope after this lecture this will be clear. So, variable declarations you've seen many times. We can have an integer, we can have a float, and the problem is that we still have no idea what goes on under the hood, right? So we just say integer, and we just trust the C++ to generate machine code for us and make sure that we can actually read an integer or a float and can work with them as with an integer or a float. So let's fix that, and let's try to understand what they actually are. So to start off, there is this kind of a very small and it's not really precise table of how you can represent numbers. So the numbers can roughly be divided into alphanumerical and numerical. So alphanumerical are they're the character, this char or car, I don't know, some people call it in different ways. So this represents a single character. So you have a string, a single character of that string will be this char. Okay? And it's a very used type. It's not intuitive why people use it so much, but the idea why people use it so much is because it is exactly 1 byte. And 1 byte is like the smallest, well, unless, not the smallest, but one of the, so it's 8 bits, and it's 1 chunk of your memory. So this is the smallest indexable part of your memory. And if you want to make sure that you can have one kind of cell in your memory on your hard drive or in your RAM, char is the type for you, and that's why people use it. We will not focus on it now a lot. We will more go into integers and floating point numbers, but that's that. So then the numerical types, they are divided into integers and the floating points. And the integers, they take 4 bytes. So they're 4 times bigger than this type over here. And alternatively to integer, you can use this type, which is more explicit, because the size of the types in C++ is not strictly defined. It's, so the C++ is a standard. And then the different people who implement the compilers and so on, they can implement their standard, their version of standard. And on most systems, integer will actually be 4 bytes, but not on all systems. There are other systems where integer will be 2 bytes or 8 bytes and so on. But usually it's 4 bytes. If you want to be sure, use this type. This way you guarantee that it's going to be 4 bytes. And then in the floating point world, so if we don't want some integer numbers like 1, 2, 3, and we want to say represent a pi, then we will need either float or double. Float is the single precision, and double is double precision. So float comes from floating point number, and double comes from double precision. Okay, so that's the naming scheme. And the float is 4 bytes, just like integer. And double is 8 bytes, so it's twice as big as the floating point number. And we are going to dive deep into that and how they are actually represented in memory. Right, so you can ask how much memory does a particular type need. So if I say, so for that there is a function sizeOf, this one. And you can call it at any point of time in your program. Let me just remove this one. We don't need it. So let's say I want a size of int. So I can do either this, or alternatively, I can pass an object into it. So int I equals 10, and then I can do the same thing, but instead of int here, I will just pass I. And if I build it, it will tell me that both of them have size of 4, so they're both 4 bytes. So in our system, int is implemented in the way we expect it to be, and so our integer is 4 bytes. Good. So a small kind of reminder on what are these bytes, bits, and so on for those who are not working with this every day. So the smallest thing that you can have is a bit. That's like the smallest cell, like physical cell in your memory. And it's either 0 or 1. There is nothing else there. So we live in a binary world where, so whenever you see like those, like in the movies where there's like zeros and ones flying around, where somebody's like doing some weird hacking and so on, that's what it comes from. That's because the whole memory is just zeros and ones, and our computer is just insanely fast to chunk through a lot of this data to do something useful for us. Now, working with zeros and ones, while possible, it's really, really not the thing that you want to do, or you want your friends to do, maybe your enemies, but not your friends. So what you want is you want to combine that into something more useful. For that, there is byte, and byte is the smallest really usable thing. Like so your memory will be like a big chunk of bytes, and every byte will have a number. And that's how memory, like RAM, is implemented. We will talk about it a bit later. And then you can pack them together because there are going to be millions and billions of those bytes, and you don't want to always say, well, I need to copy this 1 billion bytes into somewhere. You don't really care about that. That's why people have invented the kilobyte, the megabyte, the gigabyte, and the terabyte. These are the things that you're probably more comfortable with, because whenever you buy a laptop, that's what you get, right? But it just tells you how many bits is there. And it's defined like this. So now that we are on the same page with the numberings and with the type names, we can actually, So this is a small table. I will probably not go into it. A lot of types, all the size-offs of those types. This is the typical, like on a typical system, on your system, it probably will be exactly like that. But then again, do it on your own, copy that into some main function, try it out. It's gonna work for you. Good. So now we're getting into representing the things in memory. So how does a string of ones and zeros can become an integer, a useful like integer, say, I don't know, like 37, for example? The idea of this is, so first of all, so in this small example, I will not work with integer itself, but I will work with a short integer. A short integer is twice as short as a typical integer. It's just 2 bytes or 16 bits. Should be bits. Okay. You can show it like this. So you can say, this is my integer. This is 1 byte. 1 byte is 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. And another one is another 8 bits, and this is my second byte. So this is the representation of this short, unsigned short integer k. So it doesn't have a sign, it's just 2 bytes, and we want to represent 37. How do we do it? With integers, it's relatively simple. Like the moment you know what a binary system is, you're good. And what it does is basically, you start counting from here up to here, and you start with 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. This is just a convenient table for you not to compute it on your own. But then what you do is you say, well, if there is a 1 over here, then we multiply it by 2 to the power of 0. If there would be a 1 over here, we would multiply it by this. So what we do is we multiply this by this, plus this by this, plus this by this, plus this by this, and so on. And this is a very boring task. We don't want to do it. We let the computer do it usually. So, and in the end, you get a 37 by this. So you say 1 by 2 to the power of 0, 1 by 2 to the power of 2, 1 by 2 to the power of 5. And then all the zeros in front of it, which will give you 37. That's the way they're implemented. So there is no magic. This is what happens under the hood all the time. Again, you will never need to do it by hand in this course. I've been doing courses in my life where I had to do it by hand, and I hated every moment of it. I will not force you to do it. But you must understand what is going on there. So it's a good idea to know what is happening there.
What do you mean by short integer?
By what?
Short integer.
It's just another type. So there are many types. There is type integer, there is type unsigned integer, there is type short integer, there is type unsigned short integer.
What's the difference with integer?
It's twice as small. So a typical integer would have 4 bytes. It would have another 2 bytes over here. What does it mean? It means that you can represent much bigger numbers. So what is the biggest number you can represent here? Like when would be, like, how would the biggest number that we can represent in an unsigned short look like? So any ideas? Yeah.
Double, 2 times the 32,768 minus 1.
Correct. So all ones over here, right? Like if we would, that's as good as we can do. Like we can't do anything else. We only have 1 is the biggest number that can be put into every of the boxes. And so we just fill all the boxes with the maximum number that we can, which is 1, which will give us this plus all of those. And all of those are exactly this, but minus 1 exactly. So that's the maximum number that you can represent. And if you are using integer, you would have not 2 bytes of those, but you would have 4 bytes, which would make a number that you can represent much, 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 much bigger because it grows exponentially with the 2 to the power of something, right? So 2 to the power of 15 is the biggest register of this number, but it would be 2 to the power of 31 in the integer case. Okay? So that's the idea. I only used here short because I wanted it to fit on the slide. I could not fit properly 4 bytes on the slide, so I had to improvise and go with the 2 byte size. But I still wanted you to have a real type on the screen. So this is like exactly a representation of the number. Good. What we were talking about just right now, there are short integer. Yeah, right. One more thing. Whenever you have a sign, so this is an unsigned short integer, so it cannot be minus 1. If you want your say short integer to be minus 1, you have to drop the unsigned part, and then it will be a signed or a typical short integer, but you give up a lot for it. You actually give up 1 register. So then this register will be a sign. So now you don't have 2 to the power of 15, you only have 2 to the power of 14 as your maximum, as your highest register, because 1 is just given away for the sign, right? So that's how you implement the negative and the positive numbers. Yeah?
I think the sum is 26.
The sum is what?
26.
So 2 to the power of 5 is 32.
And just, 7 is 1, 1, 1. And 2 and 3 is 1, 1, not 1, 0. But divided into two parts, 4 bits. Second one is 2, and first one is.
I'm not really sure what you're telling now, but what I am sure is that this gives me 32, this gives me 4, and this gives me 1, right? So then 32 plus 4 plus 1 should be 37. But feel free to check that. There might be errors here, but there shouldn't be. All right, so the ranges. So because you have to give up the ranges, because you have to give up one box for a sign, whenever you have a signed thing, you can only have it from minus 2 to the power of 15 to up to 2 to the power of 15. And the same goes for integer, and the unsigned is a bit bigger, but only in one direction. And you can also have a long integer. So a long integer is just like short integer, but it's not shorter, but longer, right? So it's twice as long as a typical integer. Therefore, it can represent like huge numbers. This is a huge number over here. Okay, I hope that is clear. So the number that you can represent with integer is completely defined by how many bytes it has, and the way it's computed is relatively simple. It's just like on the previous slide. Yeah, so there we come to an issue. Like our floating point number is also 4 bytes. So how come can floating point number represent so much more? How come we can represent any number with floating point number? And that's when it becomes kind of complicated because you still have all those 4 bytes for you, but you now have to treat them in a different way to make sure that you can represent rational numbers, right? So if we would want to represent the, say, pi as a float number, it takes the same 4 bytes, the same 32 bits, just as a typical integer, but suddenly it can represent all those numbers. And the idea is that it's represented in memory like this. So there are 4 bytes over here. There are a lot of ones and zeros, and you have the separation of into parts. And these parts are generate a different number, are computed in a different way. We are going to go into that in a little bit, and they have different names. So we have a sign bit, then we have an exponent, and we have a mantissa. These are the typical names that you see in the float representation. The idea is that this division allows us to use the same 4 bytes, but for a lot more than we were using them for. Right, so let's try to dive into that a bit. Again, like it's not very important, but you need to understand approximately what is going on here and how to detect that you have an issue that can be solved by this. So you need to understand what is the limitation here. Right, so for example, for the pi number, right? So like we're still working with this number pi. This is actually the representation of the pi as a float, as it is in the memory. Good. So what can you do is you say, well, my exponent is 1, and then the mantissa is some other number. So how do you compute them? Well, first of all, you look at the sign. Sign is really simple. It's either 1 or 0. If it's 0, it means it's a plus, I guess. Let me check. Yeah, it's a plus. If it's a 1, it's a minus, and we're going to come to that. Then exponent is computed in exactly the same way as an integer, but minus 127. It's just the way it's defined. Again, like the good part for you is you don't have to really remember this. Like I never remember that you need to subtract 127, even though there is a reason for that. But anyway, the idea is that you compute it just like a normal number, but then you subtract 127, and it's because it's exactly half of what you can get, so you can have negative and positive numbers over there. And in this particular case, it's going to be a 1. Yeah, so exactly 1.
What kind of float is it? Double float or?
It's a typical float.
No, pi. I mean pi. What kind of float is it?
What do you mean? What kind of float?
This number pi, is it a double float or?
No, it's like whenever you see float over here, this is actually a float. So it's a typical float. There are 2 types: float and double. So float is one type, double is another type. Double is twice as big as float.
Just in the representation of the bytes.
Yeah, it's just like double. I have one slide about double afterwards. For now, we're only focusing on floats because again, it's less bytes. It's easier to explain. So I only have 4 bytes to show on the screen instead of showing you 8 bytes on the screen. Okay. Good. Then we compute the mantissa, and mantissa is the interesting part. Like it's very different from what we had in the integer, because this is the way it's computed. So it's 1 by 1 divided by 2 to the power of something, and this is just needed to give us this the rational part of our number, because this cannot give us a rational number. this cannot give us a rational number, so the only rational part of it is the mantissa. And then to compute the number itself, we use this formula. So our k would be our number. So we have the -1 to the power of the sign. So when it's 0, it's positive. When it's 1, it's negative. Then 2 to the power of the exponent. So that's the way we make our numbers big. And then we multiply by a mantissa, which is one constant that makes it rational. So in this particular case, we would have our exponent is 1, so this is just 2, this is 1, and this is 157 something, so exactly half of the pi. So if we multiply 2 by half of the pi, we get the whole pi. Good. Okay. So, and the cool part of it is that we now can represent huge intervals of numbers. So in binary it's like this, but in decimal it's insanely big numbers. So you can go from you can go plus minus, it doesn't matter, and the smallest number that you can represent is 1.2 to the power of multiplied by 10 to the power of -38, and you can go up to the 3.4 by the power of multiplied by 10 to the power of 38 again. It's a huge number, right? So the range is insane compared to the integer. And the only issue here is that, no, it's not, the issue will be on the next slide. For now, kind of answering your question, double, it's represented exactly in the same way. Just exactly in the same way, but the exponent is another 3 bits longer than in float, and the mantissa is another 30 bits longer than in float. But that's it. So mantissa would be another 30 bits there, and the exponent would be another 3 bits bigger, right? So that's the whole difference to double. And that's why in double you can represent much more, even bigger numbers, even bigger range, but you trade more memory for it. So every double number takes twice as much memory as a floating point number. Good.
Do we need to know this when we are writing?
No, you don't need to know ranges. You need to know where to look them up.
I mean, should we know that now we have to use double float or just float?
Yeah, so this, you don't, like, nobody will ask you when to use it, really, but you need to understand the issues that you can come up, that you can meet with using one or the other. Like, and again, we are going to talk about the issues that are actually practical in a couple of slides. So these practical issues are important, and the underlying math or why it's happening like that is the thing that will help you understand why that makes sense. Why it makes sense that you're losing precision in your float if you say add a pi to 10 million. Like if you add a pi to 10 million, there will be errors. And you have to understand why, because otherwise it's impossible for you to find a bug, right? So if you say have 10 million and then you add pi to it, you will have a result of 10,000,003, not 10,003.14 something. And to understand why, you need to understand this at least to some degree. At least you have to know, okay, I remember there was something about float precision, and I know where to look it up, so I can look it up and understand why it doesn't work. Because otherwise, if you don't know that, it's impossible for you to find this bug. Because you will not expect that the numbers don't work the way you want them to work, but sometimes they don't. So let me finish this part, and then if you still have those questions, we can discuss them, okay? Right, so this is what I've been talking about a lot. So we have integer and float, they're both 4 bytes. They have their own respective ranges, and you can see that the range of representation of a float is much, much, much bigger than the range of representation of the integer. Also, yeah, sorry, this is wrong. This is not the integer. It's probably the unsigned integer or something, because it starts from 0. We'll fix that. Good. So where does it come from? What do we have to give up to make sure that we can represent that huge range? And we give up precision for representation of huge range. Why does it happen? So in float, there are two parts, this exponent and mantissa, right? In integer, we can count with increment of 1, starting from whatever, from 0 up to any other number. We can just add 1 to it, and all of those numbers will be represented. So the increment is 1, the minimum increment that we can do in integer. The increment in float is not, the minimum increment in float is not really defined. It depends on the magnitude of the exponent. So the bigger the exponent, the bigger is the step that the minimum step that you can do in representing the next number. So kind of the step from one number to another depends on how big your exponent is. If your exponent is really big, your step will be bigger than if it's smaller. We're going to see it in an example soon. Right, and mantissa is 23 bits long, and it has just 8 significant numbers in the decimal representation. So 8 significant digits. So that means that anything after the 8 digits is thrown away. Right, so example. If we say take 10 million and we add pi to 10 million, what will happen? So 10 million has a mantissa that looks like this. And pi has a mantissa that looks like this. Both of them are 8 digits. And this is our comma line, okay? So we cannot have more digits in float because we're limited by the size of the mantissa. So that's the way. Like, we need all of our 8 digits to represent 10 million. We need all of our 8 digits to represent pi. And now we want to add them. And we cannot drop anything from this side because these are very significant numbers. Like, we cannot just drop this 1 because now our number becomes a 3 instead of 10 million 3. So the only place that we can drop numbers from is from the right. So we add those. We now have not 8 significant numbers, but whatever, 15 significant numbers. But we cannot hold 15 significant numbers in a float. So the only way for us to do it is to drop numbers from the right. So we do that, and in the end, the issue is that if we add a pi to 10 million, we will get 10 million 3 and not 10 million 314. And this is a very drastic example. It's a very, you kind of feel that it's really bad, and you can probably measure that this is really bad. But let's say it's not 10 million, but it's 1 million. Then you're losing, like, you're now going to have like 3.1 instead of 314. Or what if it's not 1 million, but 100,000? So if you add 100,000 in a pi, you will have 314, which looks correct. Like, everybody knows pi is 314, right? But the problem is that all the other numbers have gone away, so you've lost some precision. And this is what happens with float. Like, when you're working with float, you need to make sure that you are working in approximately the same range. The moment you're adding huge numbers to small numbers, you might go into issues where small numbers get destroyed by it. So just to show you that that I'm not lying to you, let us try to do this example. So let's say there is a float. Let's do the 314 example, and in float. That's dumb. Good. So, and let's have whatever, float I, 10 million or whatever, 1E7, 10 million. Good. Now what we want to do is we can print the pi. Also, let's probably make it. So we can use mpi from CMath. It just defines pi much better than we can, because I remember maybe 4 digits of pi, but they know much more. Good. So we can show the pi, we can show the I, and now what we can do is we can show the difference, or like the sum of them. And the sum will be I plus pi. And let's see what it brings us. Yeah. Come on. So if I run this, okay, this is, let's use the other representation. Oh, come on. How do I, okay, let's do the, that was unexpected, so I will have to add some more code to it. Set precision. Yeah, okay. Whatever. Let's have 20. So it will now show us anything that is with precision up to 20 characters, up to 20 digits. But if they're all 0, it will cut them off. So if they're like, if all the digits after the comma or after some time after the comma are 0, so it will cut them off. It won't show us all the zeros. Okay, so our floating point number is defined like this. Our integer, sorry, not integer, our big number is defined like this, so it's 10 million, and if we sum them up, we get 10,000,003, right? And again, like if we have not 10 million but 1 million, you will have some other issues like over here. So it's not 314, right? It's far, and it's because we lose precision. And if you're wondering why it's not 3.1 or something, that's because it doesn't scale linearly, right? So it depends on how many bits is the mantissa and how many bits is the exponent, and generally it's a bit confusing to think about it. So if you, like, it takes time to figure out why exactly is this the case, but the idea is that it's always just because of that formula that I showed you before of how to compute the float. And so this is basically why I'm talking about this to you. You need to know that when you're working with float and you're adding big numbers to small numbers, you might get into issues. And you need to approximately understand what can you allow to do to yourself and what you cannot, what you shouldn't do, right? So that's kind of the that is the main idea of why I'm telling this to you. And again, I've seen that a bunch of people have already ran into some issues with that when using when doing the exercise with the histogram. So if you're doing the division for every single number, you get really, really small numbers, and you sum these small numbers together, the result will be different if you sum the big numbers together and then you divide them once. It's just because of the precision of float. So whenever you feel like you're running into precision issues, you should go to use double. Yeah.
Can I store 1 billion float?
No, I don't think so. It's hard to say. That's 100 million. I mean, depends. It's hard to think when you're doing a lecture, so I can't think now. But if you try to, I mean, what you can do is you can just try to plug that into this formula over here. If it works out, you can do it, but you will probably lose a lot of precision because you only have 8 digits, right? So everything after 8 digits will be cut off. If these 8 digits happen to be after the comma, you're lucky. If they're not after the comma, you're going to lose real numbers somehow, right? So I think you can represent it, but I don't think it's really useful. But then again, I never really ran into those issues because it's already kind of like a feeling that the numbers are too big, I should use double, or like if I'm working with a lot of really, really small numbers, then I should probably also use double or something like that. But generally, if you don't care about runtime, use double. If you care about runtime, use float unless you need to use double, because double is twice slower to copy because it's twice more memory. All right. This is exactly the example. You can copy it, try it out. It's gonna work for you, I guess. So, and now that we know how the numbers are represented, that's all about numbers. So that's all that you need to know about numbers for now. Not really much to it. Like, it's just they're stored in the boxes in your memory. I want to talk to you a bit about the C-style arrays. So these are the arrays that were there before C++. They were there since 70s, and they are underlying power behind the std array, std vector, std string, and so on. So all of those are stored in a C-style array somewhere where you don't see that. Okay, so the idea is that the length of this array is fixed, and the indexing begins with 0, just as you are used to in vectors and arrays and strings and so on. And the main thing that you need to remember, like the really, really main thing, is that all the elements lie continuously in memory. Again, this is part of the lecture which you should never be using these. Like these are old style. If you want to make sure you're using something that doesn't change in size and it is an array, use a std array. There are modern types that are much more safe to use, that will tell you a lot more if you're trying to do something wrong. So don't use these arrays on a general basis. But I think it's still important to understand what they mean. Right, so they're just simple containers. You can just store a bunch of elements in them. If you say it's going to be this is the way I define an array of integers. Why is it called shorts? I think that should have been short before. Anyway, sorry. So let's say this is an array of integers, and there are 5 of them, and I give 5 of them. If I omit this number, it will just infer it from whatever I give to it, and then I can set any number with square brackets, just as you are probably already used to in vector and array. This is not a class. Like it is. Yeah. So they were there before classes arrived in C++. They were in C. There were no classes. It was just an array that puts things together into one continuous chunk of memory. They have no methods. They have no size. They don't store their size, and that's why they're kind of. If you want to pass them to a function, there is no way of knowing in the function what's the size of the array that you're passing. And you can read any memory that you want, and this is dangerous, so don't use them, but still understand that it's just some variables in a continuous memory. So it's one integer after another, after another, after another, without any gaps. That is important. Again, it doesn't store size, so you can get size of a vector by using sizeof, for example. It's a hack. Again, this is not needed in modern C++, but it's just to show that it actually works. You can say a sizeof of a vector, and of this C-style array, and it will actually give you the sizes of all the elements in it. So it will basically tell us it's going to be a size of a single type, multiplied by the size of the array, even though we don't know it, but the sizeof knows it. And if you divide the sizeof of the whole array by the size of the type, you're going to have the number of elements in the array. But this is just to show off how the sizeof works. It's not really. So I don't expect to see any code like this in your homework assignments, so don't use it. But remember that it's in continuous memory. Speaking of memory, so memory or RAM. So RAM stands for random access memory. It means that we can read and write to any single byte in the memory independently. So if I want to write now into the byte 0, well, I can't write in the byte 0, but say into byte 10,000, I can write into byte 10,000. If I want to write into byte 2 billion, I can write into byte 2 billion. And the memory, or the working memory which we're using, it has linear addressing. So it means that you can think of it as a single ribbon with boxes with bytes in it, and every byte has a number. And it's just a single, like, long ribbon with every box numbered, right? So whenever you want to put something in a box, you say, hey, I want to put this into that box with some number. And because these numbers get huge and they get really long in decimal, people use this hexadecimal system, so it's just a base 16. So we're always communicating in base 10, so 1, 2, 3, 4, 5, 6, and so on, till 10. They do the same thing, but till 16, and as we run out of numbers, we have to use letters. So it's like 0, 1, 2, 3, 4, 5 till 9, and then A, B, C, D, E, F. Okay? So these are our numbers for the 16, for the hexadecimal form. Again, it's not too important to be able to convert them from one to another. It's important to understand approximately what it means, because if you are debugging something and you're looking into your memory and you want to understand that this follows this and that follows that, it's helpful. But for that, you can also just use a calculator. Like in Linux, a calculator has a programmer's mode. Just put it in, say, compute me a decimal number, and there you're going to get it. So the important part is the pointer. So the pointer is the big topic we're going to talk about it this lecture, next lectures. And we're going to start with the raw pointers. And so the official name that we will use in this course is raw non-owning pointers. In old C++, like, they are just pointers. They were the only way. Now there are better ways to manage your memory, so they are just pointing somewhere. The idea is that you can specify a pointer to any type by just putting a star after the type. So not after the name of the function, not anywhere, it's just before, like, after the name of the type. So for instance, like a pointer to an integer would be integer pointer A, and then you set it to something. The important thing in C++ about pointers is that they're just storing address of where things lie in memory. But in addition to that, they also remember which type do they point to. So you cannot point to double and then assign the same pointer to point to an integer. It will complain, it will say, yeah, but I'm a pointer who points to double, so please give me double. I cannot point to integer. Right. We were talking about using uninitialized variables and how bad it is. Well, it's even worse with pointers, because if you leave your pointer uninitialized, this is like, it cries for disaster. Most of the bugs, like I would assume, okay, 90% of my bugs were because I didn't initialize some pointer which I should have initialized. So try to make it like really, really important to remember always to initialize a pointer, because the problem is that if you don't initialize it, it's just another variable of type pointer. It will get initialized randomly, more or less, to a random byte in your memory, and there will be something lying in that byte. You don't know what, but there will be something. And if you say, well, I am a pointer to integer, it's like if you have a hammer, everything looks like a nail, right? If I'm a pointer to integer, anything that you point me to, I will interpret it as an integer. I don't care what there is. It can be part of your big double, it can be part of your point class, it can be anything. If I think it's an integer, I will use it as an integer. So then when you try to use this pointer, it will actually interpret those bytes as an integer, just the way we already discussed today, and it will be just garbage integer. It will be just garbage number that you don't know what there means. So it's very painful to debug. It's much easier to always initialize them. So just make it a rule, never ever create a pointer without initialization. The good part is that there is a helpful pointer, null pointer. and it just points to the place where which you cannot use. Whenever you try to use a pointer that points to null pointer, you get a segmentation fault. So you get a failure, your program fails, but at least it fails. Like at least you know you've done something wrong and it doesn't use some value silently. So always, whenever you create a pointer, if you don't have anything to initialize it with the null pointer. Speaking about the initialization, okay, we will speak about initialization. This is a new slide that I added, forgot about it. The pointers that we are talking about in this lectures are non-owning pointers. So this is a very important part because what is it like? Let's remind ourselves what does owning means. Owning means like if I own a variable, I am responsible for removing this variable, for cleaning up its memory. Usually in our examples before it was a stack, so not a stack like the scope. If we create a variable in a scope, this scope is responsible for removing this variable in the end. If I create a variable in a class, this class or like the object of this class is responsible for removing this variable the moment the object goes out of scope, right? The moment somebody removes the object, and so on. So ownership equals removing. Like whoever removes something is owning it. And we will talk about pointers here which are non-owning. So they will not remove any data. They will just point to already existing data and they will expect somebody else to clean it up for them. Okay? It's a very general rule that we will obey in this course forever, that raw pointers should never own data. They're never responsible for removing any data. There are better ways of managing memory now in C++11. Before you had to manage your memory by hand. Now you don't have to do it. There are much better ways. For that we will talk about smart pointers next week. Good. We're gonna tap into this 15 minutes. I'm sorry for that, but I think it's important to finish this part before the next week. Right, so there is an operator, this ampersand. You've seen it as a reference before. If you put it before your variable, so not after a type, but before a variable, it's going to return the address of this variable. So wherever it lies in memory, it's going to return its address. So for example, if I create an integer a and then I create a pointer to an integer a pointer, I can set it to the address of this integer. How does it look in memory? It looks something like this. So I create an integer a and its address is 3, for example, just for the sake of example. And so this is what the address of A gives me. And then somewhere else, I create the integer pointer, a pointer, which is just another variable. So a pointer is just a variable of type pointer to something. Okay? Pointer is a type. So think about it. The star is part of the type. It's not some just kind of you can actually think about pointers just as about references. The only difference between the pointers and the reference is that reference cannot point to nothing. Like reference always points to a valid object, right? While the pointers can point to null pointer, so to nothing, right? Okay, so this is the memory that we use to store the pointer itself. And this pointer itself stores the value of the address of A. And that's it. So that's kind of what it's all about. Pointers are usually 8 bytes. So we have 8 bytes for a pointer, and we have 4 bytes for an integer, and that's that. I hope that is clear. But just to make sure that we all understand what is going on there, we can also have a pointer to something, right? Or a pointer to a pointer to a pointer. And, you know, you can go arbitrarily deep into that. So let's just do this small example over here. We start with A. We have an A pointer. They are still here, just as before. And then we also do a int double pointer. So it's a pointer. So you can think it's a pointer to a pointer to integer. Okay? So always read it from right to left, and then you're going to be okay. And it also just stores the address of this variable over here. So what happens here? So we create an integer a. Its address is stored in this guy over here, which itself is stored here. The address of this guy here is stored over here. So this is the pointer, this is the pointer, this is the integer. Okay? Are you following? Like, does it make sense? Okay, cool. That's all that you need to know about pointers, really, about raw pointers, about how they're stored in memory. Now, we haven't talked about how to use them, right? So to use them, you need to dereference them. And this is kind of the thing that is usually very, like for any beginner in C++, it's annoying because you have a lot of those stars and people get confused when to use them and so on. So whenever you want a value under the pointer, you can get this value by putting a star before the variable name. So I think I will have a bunch of examples later. And the thing to remember here is that whenever you try to dereference a null pointer, you will get a segmentation fault. And your program will stop running, and it will write you segmentation fault. Whenever you see segmentation fault, it means that you've tried to dereference a null pointer. It's as simple as that. Again, if you try to dereference the uninitialized pointer, it's undefined. You have no idea what will actually happen there. So it might work. It might give you some value that you don't know which value it will be, but might also actually fail if by chance that particular part of memory was pointing to 0 or to null. Okay, so how does it look like? This is a small example. Again, this is my favorite A42, and then there's a pointer to it, and the new line is over here. So let's say we want to create a copy of A, but we like living dangerously, so we do it through a pointer. Right? It's just an illustrative example. It's not useful in any way. But if we put this star over here, so before the pointer, we get the value of the thing that the pointer points to. Okay? So B will now be actually 42, because we know that the pointer points to the A variable, and the A variable has a value of 42. So now if we dereference this pointer, we get the value of B equals to the value of A. How to remember where to put the star? If you declare a pointer, a star goes after the type. So think about star, like whenever you put a star after a type, it means this is not your type anymore, it's a pointer to this type. Okay? So if you declare a new variable and you put a star after a type, you've declared a new pointer. If you're just using a star before a variable without a type, without declaring a new variable, then you're dereferencing the pointer. That's it. That's all you need to know about the star operator in the pointers. Right. Also, it returns you an L value, which means you can modify it. So if you do a star A pointer and you set it to 13, for example, you would get you would actually change the value of A. So again, think about it just as about references, just with a bit more explicit syntax. So now you have to say, yeah, dereference this for me and set it to this value. Before, if this all were just references, we could create a reference to an A without all those signs over here, and then we would say A reference equals 13. It would still work exactly in the same way. So if you kind of understand references, then this is exactly like that, but with some additional syntax. And we... which one? You mean?
That one with dereferencing the next one. No, not here. Yes, this one.
This one, okay.
Then when you say that we encounter segmentation fault, why did you do it in the next slide?
No. Like, it's only if I dereference a null pointer. So if I would say integer star a pointer equals null pointer, so null pointer is just think of it as a zero of pointers, right? So it points to some place which is guaranteed to have nothing, there. So whenever you try to dereference it, your program will stop. You want this guarantee. That's as much as you want. So if I wouldn't have this a to set here, I would initialize it with null pointer, but then I wouldn't dereference it because I cannot dereference a null pointer. Okay?
Dereferencing means using it.
Yes, dereferencing means getting a value. So I have a pointer that points to some value. To get that value, I need to dereference this pointer. All right. So a small example for the uninitialized pointer. I don't have the time to run it live for you, but I hope you believe that this is exactly how it works. And again, if you copy it, try it, you will see something like it. So let's say I create an uninitialized pointer over here, right? So I left it uninitialized, I made a mistake. If I just ask it for address, it will give me some address. It's going to be some address. I have no idea which address it will be. It can be 0 if you're lucky, but if you're not lucky, it's going to be some address, some random address. And if I ask about a value under this address, it can actually be some value over there, and this value will be garbage, as I told you. Most of the times, it's going to be 0, because most of the memory is 0. But it's not always the case, and that's why this bug is hard to catch. So if this would happen in a real program, and I would dereference it and use this number, I would be really, it would be really strange why say, I don't know, my index is wrong or something like that. You know, you have all the consequences that you cannot measure really, that you don't know what the cause for them is, because you didn't initialize the pointer. Right, so if so what I need to do is I need to set it to null pointer, and if I ask for the address of the null pointer, it will give me a 0. And if I would try to dereference it, I would get a segmentation fault, which is what I want. Like, I don't want to dereference a null pointer, but if I do, it's a mistake in my program. I just need to go back to it and fix it. Good. Right. So again, like a small recap, like I keep repeating these things because they're really important. So always initialize them, and whenever you try to dereference a null pointer, it's a segmentation fault. But then to avoid segmentation faults, you can actually now check if you actually have a pointer, like if your pointer points to something useful, and you just do it with an if. You could write it, if my pointer is not equal to null pointer, you could write that. But there is a shorter syntax for that. You can just say, if a pointer, then do something. And this way you guarantee that this code will only be executed if some pointer is not a null pointer. And again, if you want to make sure that your pointer, to run something that is always, like when something is a null pointer, you just do a not some pointer, and this will only enter this cycle if this is actually a null pointer. Right, okay, I think this, okay, there are 2 more slides. Yeah. Right, so as I told you that the array elements are continuous in memory, so it looks something like this. You would have some name of the array over here, and then you would have all the variables of the array in the continuous memory. So if I say, these are all doubles, for example, so 8 bytes each of them, and let's say I create a double array of 3 elements, I can actually navigate it with pointers. So an array is just an alias to a pointer. It's just a fancy way of defining it. So I can easily say double star something equals this array, or the same thing goes for give me the address of the first element of this array. That's basically it. It's just like to connect these 2 concepts in your head a bit. The thing that you might, like, it's again illustrating that memory is just a continuous chunk of boxes that store some value. So if I create an array of 3 elements of integers, but then I iterate up to 6 elements instead of 3, what will happen? So I will have my 0 index, which will give me a value of 1, index 1, which will give me a value of 2, and again, these are the addresses. And you can see that, like, probably you don't yet know how to read this 16 base numbers, but you can see that the address of this ends with 0, this one in 4, because an integer is 4 bytes. So the address is 4 bytes further than this address. And this one is 4 bytes further than this address, and so on. Good, so everything is good until this point, but then suddenly we try to get a value that is not in our array anymore, but the program will not stop. It will not tell us that we're doing something wrong. It usually will just continue going, and it will try to interpret whatever there is as an integer, and by chance it would be a 0. Then the 4th element will be whatever this number is, and then the 5th one will be something like this. And it can be arbitrary garbage. If you run it on your machine, it will probably also run, but it will give you other values which also will be garbage. So be careful with your indexing. And that's why, like, you should always use a range for loop if you can, and so on, because this way you cannot, like, overshoot your arrays or something. And the last thing that I want to tell you about is how the custom objects are stored in memory. So it's not guaranteed how the compiler will do it. It can move things around and pack them in memory the way it wants to when it tries to optimize things. Usually they're stored sequentially. So usually if you have an integer here, a double here, and another float over here, they will be stored sequentially in the memory. Functions are not stored in memory. They are not in memory. They are just some executable code that will be generated for you, but they are not stored in memory. And just a small example. So again, you can run it. I will not go through it. The idea is that there was an integer, there was a double, and there was a float in our class. And if you just output the size of and all the addresses, you can actually see where the things are actually stored in the memory. And it's actually going to be like 4 bytes for integer. Then the compiler thinks it's a good idea to add some padding, so there's going to be nothing there. And then it's going to add a double, and so on. So it's just to give you a hint that whenever you create a class, most of the times the things will be stored approximately sequentially in memory, but some padding can be added. So that there is no magic. Like, your classes are just a collection of data that is stored together in memory. So every object is stored together in memory. Okay, that's it. Sorry for taking so long.